Now I'm going to give some practical examples. Okay, here are some examples in order to know the Simulink applications. Most of them are mathematical equations in order to understand simulation of mathematical equations. As I said in the previous chapter, the basis of simulation is that first you should find your system, then model it mathematically, and after that you can use that mathematical model in your simulation. Well, now I go into the mathematical equation to implement it in the Simulink. The equation is x different derivative equals 10 sinus t, which is time here. In such equations, as you know, the answer is integral of 10 sinus t. It means that x is going to be simulated, and integral of 10 sinus t should be simulated. I create a new model in the Simulink. Then I should enter the blocks here. For this equation, we need sinus source, integration, and a displayer to show the output. In doing so, because our source input is sinus, I go to these sources, and in source library you can find most of the sources for your simulation. For example, here there is a source input named step. You can use time, constant block, random number, or a random function which works randomly for input, or ramp and pulse generator. Or even you want a source input that is not the Simulink, but you have defined its code in MATLAB before, so you can use this block to recall the code and give it to the system as block. I add this integrator and the scope. Now I add a sinus wave source to my system. You may have question on how I can find these blocks easily. The first reason is that you should use Simulink help to find the block. The other reason is that I have worked with Simulink a lot and know the library of each block. But there are common libraries as sources, sinks, or math operation. But you should work with these blocks if you want to find blocks easily. The Simulink help can help you in this regard too. Okay, we go to the new model. As you can see, these are the selected blocks as we saw in the system. I want get the integral of sinus. So we should enter a signal from sinus wave to the integrator and then transfer its output to the scope. By double clicking on the sinus wave, you can change the amounts. For example, here in sinus type we have time based and sample based. Here you can set it on sample based or even set it time based, which uses simulation time, or you can use an output signal as time. You can set the amplitude amount here, because in this example the amount is 10. I set the amplitude 10. Here we have integrator which get the integral of input signal. Here the point is that for moving the blocks in Simulink, just click on the block and drag it. Okay, now for simulation. Our system is time-based because, as we saw, x equals 10 times integral of sinus t. Here you can set any time interval. I set it 20 seconds. I click on the run. Okay, now if you double click on the scope, you can see the wave. As you can see, it's a sinus wave. Okay, let me save it. Okay, as example 2. Okay, now we're going to simulate another example, which is a bit complex. We can say that it's a system. In fact, here I want to simulate it in Simulink and see the results. Maybe these examples have not a practical usage. They are just for understanding of Simulink applications or finding different blocks. Okay, in this system, x equals a times cosine of omega 1t plus b times cotangent of omega 2t. Well, a and b are constant numbers, 6 and 4, and omega 1 and omega 2 are determinative of frequency or sinus function period, which here are cosine and cotangent. One way to ease the simulation is that determine what blocks are needed in simulation. Let me show the procedure in the slide. Here we have A and B, which cosines multiplies in them. So A and B are gained in our simulation. Omega 1 and 2, as I said before, are determinative of cosine and cotangent function period. So we enter these values as input to these functions and use constant blocks to define them. For T, we can see Simulink simulation, use Simulink simulation time. Also, we can use extra source named clock. For cosine and cotangent, I will tell you later that what blocks should be used, but the block which we have is trigonometric function. We have plus sign, which is sum, and a scope for display, which is x, and product for multiplication of omega 1 and t. Now, in order to find the block of cosine and cotangent, there are many ways. One way is using Simulink help. The other way is using search. But this search only shows the blocks that saved with this name exactly in the Simulink libraries. For example, here in the math operation library, we have a math function block. I want to show you this function. By double clicking on the block, the information of block will be shown like this. As you can see, it shows e to the power of u. Suppose that I want to change it. For example, I want to use square function. Here, it means that u to the power of 2. Generally, this function is called math function. You can't find this block in the search section unless you use a function or math word in the search section. While, as we can see, there are much more applications in this block than what we see in its icon. I mean, a simple e to the power u. We can use square, we can use to the power 2, or many other functions which are in math. Okay, now I want to find cosine function. As you can see, just one block has been found which is related to lookup table library. Lookup table is one part of Simulink which has many usages. I will explain it later. As you can see, there is no other block. For example, now I search the sinus. As you can see, there is a sinus wave function in which t enters in it as an external function. Also, we have sinus, which is for lookup table, and we cannot use it here. Now, if I search cotangent, absolutely nothing should be found. Okay, I go to Simulink help. You will see that there will be more results here, because in Simulink help, when you search sinus, all the functions that are in a block and use sinus function will be shown. So you can find more blocks in the Simulink help section. You can have an advanced search. For example, I search sinus here, and as you can see, all the sinuses, even those which are in MATLAB, are shown. In the left side, I select the Simulink to just see the Simulink results. We can see each one separately. For example, one of them is trigonometric function. Here are the functions of this block. For example, sinus, cosine, tangent, a sinus, a cosine, sinus, hyperbolic, and etc. We cannot find this block in the Simulink search, but it has found in the Simulink help. Okay, let's look at other functions. We have FCN, which is user-defined function. If we click on the block, it asks us the intended function. Here also we have interpreted MATLAB function. It uses MATLAB function. Also we have sinus wave, which saw it before. It generates sinus wave. Also we have MATLAB function. This block helps us to define codes in Simulink. Okay, now you learned what to do in finding the blocks. As you saw, first we search in the Simulink, some blocks have shown. But to find the blocks, it's better to search in the Simulink help. We repeat the process for cosine function. I search it. There are MATLAB data here, which I want to search it in Simulink. So I select the Simulink. Again, the first option is trigonometric function. As I said before, we can use from sinus, cosine, tangent, and etc. in this function. There are other functions. We have lookup table and functions that are in user-defined function, and MATLAB function, which I explained about all of them before. So here we are going to use trigonometric function because lookup tables have a specific applications and are not used here. Using the functions that we can define codes in them are a little difficult. We will talk about them later. MATLAB function is not advanced too because we should deal with codes. The reason that I say we don't use them is that we have these blocks here. For example, if we didn't have this block, we had to use functions and coding. So the trigonometric function was shown here because it can be used for sinus, cosine, tangent, and etc. Now, how can I find it in Simulink? There are two ways. One is searching the trigonometric term. Then I can go to the library which was shown here. Before finding trigonometric function in Simulink, I want to search cotangent 2. Again, MATLAB functions have shown. I select the Simulink. In the Simulink, as you see, we don't have any block with cotangent name. It means that we don't have any block for simulation of cotangent x or t, so we should make it. In doing so, you must find its math equations or use a MATLAB function and define the codes in it. I explain it step by step later. So I close the help window. As shown in help, trigonometric function is in math operations library. As we can see, there are too many blocks here. We can search it here. Otherwise, we can look for it in the library. You can find it quickly if you use the search. So in finding the blocks, first we search it in the Simulink. Then if we couldn't find it, we go to the Simulink help. Okay, I create a new model in order to simulate our model. I add trigonometric function, constant, gain, we need it, sum, scope for our output, product for multiplication of amounts, and the clock for time. As you can see, they are accumulated on each other. In order to prevent it, you can separate each block after adding it to the new model. First function is cosine. By double-clicking on the trigonometric function, we can change its function. As you saw, all of the functions are here. I set the cosine. The inputs of our model are omega 1 and time. In order to enter them to the cosine simultaneously, we should multiply these two blocks because as we saw in the model, omega 1 times 2t. So we connect the product signal to the cosine, then I connect the signal from clock to the product. I do so for constant. Because the simulation time is 10, I enter it in the clock too, which is 10 by default. We set the constant block P, so cosine multiplies to a gain, which the amount of gain is 6. The cosine is prepared now. For cotangent, as I said, we don't have cotangent function in Simulink. In order to make it, we should use mathematical equations of cotangent. As you know, cotangent equals to cosine divided by sinus. In the Simulink, we have both sinus and cosine functions. So we can divide them and get the cotangent. I get a copy from this part and paste it here. Then I should set the amount of cotangent based on the main equation here too. Here omega 2 is 2p. I enter the 2p here. Then I should create a sinus part, so I get another copy. The sinus and cosine are equal except the cosine function, which should be changed to sinus. Now I should divide them. Okay. For this case, we must find the divide block in the Simulink. In doing so, we search and find it in math operation. Upper part is multiplication and is for cosine. The lower is division and is for sinus. After generating cotangent function, we should multiply it in gain b, which its amount was for 2. Two distinguished parts of our function have been simulated. Just here, we should plus them to get the output. As you can see here, a plus sign is bottom and another one is in the front. You can change the parts which signals enters to the block. For example, if a plus be here and another plus on the other side, one enters from the up and another one from the bottom. I use this form to plus the two signals. As I said before, the output will be x, or the desired output which we want from this mathematical function. Now, if we run the system, we should reach the desired result. The output was not very important. We just wanted to simulate the system and show the blocks. Let me save it as example 3. In the next example, I want to tell you that when we have a cosine function, how can we show its derivative integral in one shape or separately? In doing so, I make a new model in Simulink. As I said before, there are many ways to simulate cosine function, which the best way was going to math operation library and choosing trigonometric function block. Because the block should receive an input, we should assign an input to it. Which here I assign time as the input. If we want to follow the previous procedure first, we should indicate what blocks are needed. For cosine, as I said in previous example, we need a trigonometric block, a time. These two blocks are enough for cosine simulation because we don't have any amount to specify frequency or period. Then x equals integral of cosine, so we need integration block. We need an integration block. And this part equals cosine different derivative. So we need a derivative block. Because our function is continuous, we can find these two blocks in the continuous library. Derivative and integration. We give the time to sinus, which should be changed to cosine. Three signals should be exited from the cosine, one to derivative, one to integrator, and the last one to the scope. So I get a scope 2. There are two ways to show the results. One, we should use max block to show the cosine integration, cosine derivative, and cosine. You will see that it accepts several signals and has an output. By double-clicking on max, we can know how many signals it receives. You see the number of inputs here, but because we want to show 3 inputs here, I set it 3. Now as you can see, the input increase and input increase actually. One of the max input is related to the integrator. The second one is for cosine. And the third one is related to the derivative. I connect them to each other. As you can see, the 3 signals shown on a scope. This is a cosine, and these two are integrator and derivative of cosine. Now suppose that I don't want to show these signals on a single scope. I want to show them separately. In doing so, I get a copy from scope. I double click on the scope. There's an option in scope named parameters. I will explain the settings of scope and other blocks which are used to display the output later. If I click on this part, one window will be opened. In general, we have access which is related to the number of simulation displayers. If I increase it to 3, as you can see, we will have 3 shapes here. Also in the scope input, we have 3 inputs, and you can connect 3 signals to a scope block. So I close it. Now as you can see, we can enter 3 signals to the scope. I set the first input integrator, the second one cosine, and the third one derivative. I connect them here like this. Now I Run the simulation. And as we can see, it is the same, it hasn't changed. So now you can show the three functions separately. In the middle one, cosine, the first one, integrator, and the last one, or the third one, it is for the derivative. So it was an example to know how to show the outputs in Simulink. I save it as example 4. Okay, the next example is y equals 1/4 of x to the power minus x plus x to the power 2 minus 8. I create a new model. I add my blocks, math function for e to the power u, for e to the power u, because our u is minus x and should be changed, it should be changed. I use clock for the simulation. I consider the x as t. Because it's minus, I should multiply it to a minus. In doing so, there are two ways. One is getting constant and product block. I set the constant block -1, and with using a product block, multiply the constant and clock blocks. Or multiply it to a gain directly and give its output to the function. I set the gain value -1 and connect it to math function block. In the second part, we have function named x to the power 2. I use clock block for simulating x. Because the x is to the power 2, I choose square mode. I divide the first function by 1/4 and subtract 1 divided by 4 and subtract a minus 8 constant from the other functions in the last part. Now I should transfer these 3 to the sum. Our output will be y that we had in the main equation. And as you can see, there are two inputs for the sum function. As you can see, there are two inputs for the sum function. If we want to increase it, we should increase the positive signs. As you can see, the sum block's shape is not good. So here, I remove the slash or move it on the right to make the shape better. Now I connect the three inputs to the sum. So the output will be y function. This is 10 seconds of the function. Now this is the x-axis and y. By changing x, as we can see from 0 to 10, the y is changing like this. Let me save it as example 5. The last example is a nonlinear example. It is a second time nonlinear system. As you see, x dot 1 equals x1 times x2 and x dot 2 equals x1 plus u, that u is a sinus function. Let's simulate in Simulink. But as you know, it's different from the previous examples because we have a second time nonlinear system. For this example, we have two x1 and x2. So, and we should multiply them. We need a product block here. Like this. Okay, I add it. Then if we see the system, we have x2 equals x1 plus u, so we need sum. And sinus wave, which is u. I consider it from the beginning. Unlike the previous examples, x1 and x2 enters to this part. Now to specify the x1 and x2, I use a demax. In the demax block, I consider the upper signal x1 and the bottom signal x2. You can increase the size of blocks in order to have a neat modeling. As I said, the positive part comes from the x1 signal. The bottom one is x2 signal. These two enter to max because then we want to transfer them in an integrator block. The output of the mux block must enter to the input of integrator block. Okay, here we create x2.function which equals x1 plus sinus or u, and create x1 dot here that is equal x1 times x2. We can use an integrator block and connect the mux output to the integrator input. Now we should use a scope in order to show the output. Here we can divide the scope into two separate parts. As I said in the previous example, we change the number of axes to 2. Click on OK. I consider the upper figure for x1 and the bottom for x2. If I go to settings outside the source, we will see that it's working based on time. We don't change it to external. The amplitude is 1. And we accept the other amounts. As you can see now, okay, I run the system. As you can see, the x1 is 0. The reason is that x1 equals integrator of x1 and x2 and does not have any input source. Also, the conditions of x1 and x2 have been considered 0 in this simulation, while x2 equals integrator of x1 plus u, or sinus function. So the output is in sinus form. Now, in order to change x1, I change the initial function in the integrator. Pay attention that two signals have been entered to the integrator, which was done by mux. So any amount which we enter to the initial function should be set for other amounts too. How we can do that? By matrix. I set the initial function for x1, 1e to the power minus 5, and for x2 I enter 0.001. We faced error. The reason is that I have not entered the bracket at the end. One of the advantages of Simulink is that it explains why the error occurred. In the next chapter, I will talk about MATLAB and Simulink error more. But in fact, in simulation, you may face a lot of errors. In this regard, there are many reasons. One was the error we had here. The other may be related to the amounts. For example, you give an amount to a specific block and you specify that number with A. Then after running the simulation, you may face error because A is an unknown amount. I try to talk about errors later, but generally the Simulink itself explains why you have these errors. I change the initial condition, I run the simulation. As you see, because I set the initial condition for my system, the x1 of our system changes to and goes to instability. It said, if I set the time 20 seconds, oh, we have an error here. It says that our signal in the 11.71 second is not finite and simulation will be stopped. For solving this problem, I change the initial value I set it e to the power minus 3. Again, we have an error. Again, I said it, and this time lower. Now, as we can see, our system is completely unstable. I save it as example 6. In the next example, I want to simulate the system in time and Laplace area. We simulate a similar system in time area and then show that system in the Laplace area. We want to see whether the Simulink has a similar result for both or not, which absolutely should have. It means that for these two systems, we should get a single output for the Simulink. Our system is x per t equals minus 2xt plus ut, which is our input, and our ut is a square function. And in the Laplace area, our system is sx equals minus 2x plus u, which finally our x equals u divided by s plus 2. First, we simulate the system in the time area. As you saw in the system, we had a plus in the equation, so when it is sum block, the ut is a square, so when it is source function, when it is scope to show the x, and for making a square function, I use signal generator. In the next chapter, I will explain these input sources. I add a signal generator. If I double click on the signal generator, we have waveform, sinus square, sawtooth, and random. For example, I click on this square, and I use simulation time and click on OK. And other amounts are default by default. As we saw in the system, the u function adds 2x. I add the gain to my model 2. The function exists from integrator is x. If I double click on the signal, I can type x here, So it's related to this part. This gain should be equals to -2. So the output here will be -2. In this slide, I have not explained how I got integrated in time area, but you can easily understand how the system is simulated. Okay, I simulated the time area system. This is our output function. Now we want to show it in Laplace area too. In Laplace area, the x equals u divided by s plus 2. So in order to simulate this system in Laplace area, it seems that it's not very difficult. We have transfer function, which is usually used for equations of transfer functions. It is in continuous. I will explain about this block in the next chapter briefly. I add them to my system. I think it's enough, just that block. I think it's enough. We have other blocks in our model. Our input is signal generator. I copied them and their amounts haven't changed. When we copy them, the amounts, as you saw, won't be changed. If I add them new, your amounts will be changed, but if you copy the model, your amounts will be saved. Okay, I connect them. I run the simulation. Now, as we can see, these output systems are similar. We have a single output. Okay, thank you. Thanks for being with us, and bye-bye.